Hi everyone. Sorry I couldn't be there. I'm Alex Gardner from NASA's Jet Propulsion Laboratory, and I've just been asked to come and talk about what the state of satellite observations are for monitoring the ice sheet, and what does the future look like. I'm really excited to talk about it. Very sorry I couldn't be there. It would be fantastic to be sharing beers with everybody. But unfortunately, I'm on vacation with my family in Utah right now, so I'll make sure to call in so I can participate in the discussion, but otherwise I have to give the presentation remotely. So let's get started. Okay, so what's really driving all of the ice sheet research right now is simply that global temperatures are rising. They have been for the last half century, and they're going to continue to rise into the future. And this is all but certainty, and it appears like we'll be tracking the higher end of those scenarios as the world is crippled into inaction into mitigating CO2 into the atmosphere. And as the planet warms, the land ice responds and it grows and shrinks. And we live on this really interesting planet where the planet is right close to the change in phase of water. And so if the planet's just a little bit warmer, most of the ice disappears. And if the planet is just a little bit cooler, a lot of the ice is gained back. And so when we have these changes in temperature, we get large fluctuations in the amount of ice that's on land, and that changes sea levels. And that is one of the things that everybody in this room is really interested in, and we all spend a lot of time researching. And the primary focus of our research is thinking about things along the lines of what does the future hold? Well, all projections of sea level rise project that the ice sheets will melt, the oceans will warm and expand, and sea level will rise. And there's a lot of uncertainty. A lot of the uncertainty is simply due to the different emission scenarios. What pathway is humanity going to choose as we move forward over the next hundred and several hundred years? And then there's also uncertainty because of the models. And so, we don't know exactly how the change in forcing will modify the ocean, and how those changes in the ocean will modify the ice sheets and modify the surface melt and all these other things. And so there's kind of this extrinsic and intrinsic uncertainty. And, I know I'm talking to the converted here, but I always like to mention that millimeters matter. One of the earlier publications, actually with Geir Moholt, we published a paper for glacier change back in 2011, and somebody from my hometown wrote a rebuttal that how can millimeters matter? It's only the thickness of a pencil. And what he failed to recognize is that when you add millimeters together, you can get meters, and meters matter. So this is just an example for Florida under different sea level rise scenarios. And sometimes as researchers, we kind of forget that our work really does matter. There are people that live in low-lying areas that are going to be greatly impacted by sea level rise, and they're making decisions on very uncertain data. And so that's kind of where we come in, is to help try and narrow that spread given an array of emission scenarios. So if we just look at the latest IPCC assessment report, and we look at RCP 8.5, so this is kind of the upper case scenario for emissions and atmospheric forcing. But that's kind of the track that we've been following on for the last few decades, and so it's probably more realistic than not. And if we look at the different components that are going to contribute to sea level rise, we can see that it's primarily land ice. So there'll be kind of equal contributions from the Antarctic, from Greenland, and glaciers over the next 80 years, with thermal expansion taking up a large piece of that pie, and then changes in land water storage. And so as you pump more water out of the ground, it eventually finds its way into the oceans. And that's somewhat compensated for, or was compensated for in the past, by the building of dams. But what's really interesting is when you look at the uncertainty in sea level rise projections. And so there's The uncertainty, the extrinsic uncertainty, which is driven by what climate scenario do we end up following. And so let's ignore that because that's really outside of our domain, and society will determine that. But if we look at the intrinsic uncertainty, so each of the individual contributors given a projection scenario, you can see that the distribution changes greatly. And so over half of all of the uncertainty in sea level rise is driven by the Antarctic and changes in the Antarctic. And that actually doesn't include the large tipping points in the Antarctic. And so what this tells us is that if we want to improve projections of sea level rise, we really need to focus on improving projections of Antarctic ice sheet change. And that's why we're here. We're here to talk about the observations that need to be made to help bring down that piece of the pie. And then one thing we can't ignore is the fact that we are very close to these irreversible tipping points, to the fact that we really can't tell if this century we will cross a line in which we will not be able to regrow either the Antarctic ice sheet or the Greenland ice sheet in its current state. Both ice sheets are very close to tipping points. And so in Greenland, that tipping point is when the surface melt becomes so much that it modifies the surface elevation, and that lowers the ice sheet, and because of the atmospheric collapse rate, that exposes it to warmer temperatures. And so even if you reset the temperature back to pre-industrial times, you can no longer regrow the Greenland ice sheet, and it goes into a feedback loop where it just wastes away for the next 10,000 years or so. In the Antarctic, that's different. In the Antarctic, it's all about the dynamic instability or the change in flow of the ice sheet. Surface melt is not going to play as big of a role there. It may influence the ice shelves and how long the ice shelves last, but primarily it's the interaction between the ocean and the ice, and then the marine ice sheet instability that would play out after that. And so, this is very real. I recently presented this to a group from NSF, and one of the NSF program managers stopped me halfway through and said, is that real? Is that actually a thing that we might cross these tipping points? And I would argue that for Greenland, we may have already crossed this tipping point. And so, it's somewhat depressing, but it's also urgent. And time is of the essence. This is kind of common knowledge now that one of the most consequential impacts of climate change is going to be rising oceans. I think it's probably one of the most predictable as well, and I think we can do better at the prediction part, and that's why we're all here to see if we can help out with that. So, what are the major remaining sources of uncertainty in ice sheet change into the future? So what's driving that big wedge of the pie of Greenland and the Antarctic that accounts for at least 2/3 of the uncertainty in sea level change? And really what's driving it is unknown processes, so still poor understanding of some of the processes, and those processes include basal sliding, determining what those relations should be and when they should be applied. Calving and rifting, we really have a poor model representation of how calving can be predicted into the future and how rifting can be predicted into the future. Ice shelf thinning, so that's the interaction with the ocean. That's very challenging to model. The transfer coefficients between the ocean and the ice are not well known. And in addition, the changes in ocean, especially under the ice shelves, is really poorly constrained. And then one of the big observations that's missing is bedrock topography. And so if we don't have the bedrock topography, we simply can't model the future response of the ice sheet. And so it's almost a non-starter. We can improve all of the physics we want, but if we don't have an accurate bed topography, then we're going to be limited in what we can say about the future response of the ice sheet. And then there's also other sources of other sources of uncertainty. So ice atmosphere interactions and ice ocean interactions. And so we're talking about things like precipitation, how that will change in the future. That has a large impact over the Antarctic. Ice shelf melt by ocean. I've already mentioned that one. How will the surface melting over the ice shelves and also in Greenland? What are the snow, fern, ice microphysics that will influence how that meltwater is distributed across the ice sheet and how much will leave? And then also internal refreeze and densification are also processes that we're going to have to understand in order to improve our estimates of surface mass balance. Okay, so moving on to the sensors. We have lots of different ways now that we can measure the ice sheets from space, and I would argue that this has really happened hugely over the period of time since I started grad school in 2005. I think our ability to observe changes in the ice sheet was primarily looking at the old radar altimeters that were primarily designed to measure ocean height changes, but we could apply them to the ice sheets. And since then, we've had a lot more tools that we can throw at the problem, and algorithms have improved and compute power have improved. And so a couple of the key instruments that we can use to monitor the ice sheet change are the optical instruments. The workhorses for that are Landsat, the whole Landsat series, and the Sentinel-2 mission. And then there's the synthetic aperture radar missions. There's some commercial ones out there, but kind of the workhorses, the workhorse really is Sentinel-1 right now, which is the ESA series of satellites. Currently, we only have one, but hopefully within a year we'll have Sentinel-1C up so that we can continue with 2 pairs. And then we have NISAR coming, and I'll talk a bit about that later. And then we also have the ability to measure gravity from space, which is absolutely incredible. This is, when I was a professor and I taught remote sensing, every year I would start with, satellites measure some portion of the electromagnetic spectrum and gravity, so until we have a unifying theory, and gravity is just grace and grace follow-on. They're very unique measurements. And they give us this amazing ability to weigh changes on the surface of the Earth. And so changes in mass of the surface of the Earth is primarily dictated by movement of water. And the biggest trends are over the ice sheets where you have large changes in mass. And then we also have the altimeters. So we had, Cryosat-2, IceSat, IceSat-2. And I should mention right now, full disclosure, this talk is very North American centric. I am at a NASA facility, and so a lot of my work is really dedicated to NASA's observing capabilities and using those ESA satellites as well when beneficial. But it's not all encompassing, so I hope nobody's offended. Okay, and then we also have suborbital campaigns. And so Joe McGregor, who is in the audience and was lucky enough to be able to go and join in person, was the science PI for the mission, the project scientist, I should say, for the last years of the mission, and is much more expert in this area than I am. But I think, the contributions that were made by Operation Icebridge over the period in which it operated are immense. And this is just showing for the Antarctic. Obviously, there was a lot of flights over Greenland and Alaska and some over the Canadian Arctic as well. But I would say it revolutionized our understanding of the basal topography in very critical areas, and also in the near surface properties. So it also carried a Ka band snow radar. And so there was a lot of work done on the layering, and then also helped as a bridge between IceSat and IceSat-2 to provide continuity in key locations for the laser altimetry. And so, it was incredibly impressive. The total distance flown was 5 times the round trip distance between the Earth and the Moon, which I find absolutely fascinating. And Operation Icebridge was really heavily funded or funded by NASA, and it was really a NASA initiative. But it also showed a great ability to collaborate, especially in remote places like the Antarctic, where access to bases, access to resources, access to knowledge is so sparse that collaboration is really required for a successful mission. And Operation Icebridge did a really good job of reaching out to the different institutions down there, collaborating and making all of those observations possible. And then this is just talking about some of the achievements that from Operation Icebridge. This is just kind of where we were back in 2009 and how much our understanding changed by the end of the mission. And I think the amount of information that we gained from the suborbital mission was absolutely astounding. And I think it should be strong motivation for continuing this work so that we can, close the remaining gaps that exist. And I don't want to say that Operation Icebridge was the only missions that were measuring bedrock topography. Obviously, there were lots of other nations measuring bedrock topography, but I'm not going to cover those all here. Hopefully, others will cover them in their talks. Okay, this is just continuing on with the state of knowledge. I'm actually going to skip this slide. Okay, and now I'm going to talk about the kind of new era of cryosphere observations that really began in 2018 with the launch of GRACE follow-on in ICESat-2, and then also a number of initiatives. I've put my own up here, which is called ITSLive, which generates global glacier velocities, but there are lots of other efforts that are trying to generate these really comprehensive data sets so that we can understand the changes in behavior of ice sheets and glaciers. And so there's two other measures, NASA Measures Project. There's one by Eric Rignot and one by Ian Jochen. And then there's a lot of the CCI work is contributing greatly to these efforts. And so there's a lot of great kind of synthesizing efforts to try and generate better data sets to derive understanding. So this is a highlight slide. This is the elevation change measured by ICESat to ICESat-2. And this was really one of the first publications that came out of ICESat-2. And it was just, a radical change in the precision or the accuracy with which we can measure ice sheet change. The accuracy of ICESat-2 is absolutely stunning. And the number of observations that we're getting is incredible. So ICESat-1 took a measurement, it was at 70 or 150 meters along track. And ICESat-2 is taking a measurement every 0.7 meters along track. And ICESat-1 had a single beam, and ICESat-2 has 6 beams, and it resolves the across-track slope for each of those different beams. And it's really just an amazing data set to go play with. And it's revealing in great detail all of the different changes that have been observed by past missions and some of the new changes that we haven't observed before. And then there's also, this is kind of continuing on these synthesis efforts. Bed Machine, I think Mathieu Morlahan hopefully is there, but he might be presenting remotely as well. But him and his group have done a tremendous job working with the entire community to bring all of those observations together and optimally interpolate them either through mass conservation or other approaches to try and reconstruct the bed as best possible with the information that we have. And things like these data sets really fundamentally provide step changes in our ability to forward model changes in the ice sheet. And then we have GRACE and GRACE follow-on. So we start with the mass change drive from GRACE early in the record. And we have a data gap. You can see the straight line kind of post 2016 to 2018. And then it continues with GRACE follow-on. And that gap, because just because of the measurement itself, that gap doesn't influence the results much at all. As soon as you turn on GRACE follow-on and do a little bit of calibration, you're back on target to measuring the total mass change. And early studies from GRACE were really fundamental in formulating our understanding of how the mass of the ice sheet is changing. This combined with altimetry gives us really great insights into where the change is occurring, and then allow us to postulate questions around why are they changing. And then there's other novel data sets coming out. This is a data set from Chad Green. It's absolutely a stunning and beautiful data set. Chad Green is there in person today as well, and he's kind of a representative from JPL, in-person representative. And he has a paper in press right now, and this data set will be released very shortly, hopefully within the next month. It is a reconstruction of the front position all around the Antarctic ice sheet from 1997 all the way through to 2021. And what the novelty of this data set is he assimilates a whole pile of different data that's been collected, and then uses the flow of the ice sheet and kind of the known physics of the ice sheet to constrain where that ice front can exist, and that helps a lot with outlier filtering and gives this beautiful record of flow. And so this next slide, I just want to show what that looks like. And so here's a little video that Chad created for the Larsen C, and we can just watch this in real time. And it's just incredible. You can see the ice sheet is always moving forward. It's always trying to regrow. And then you can see the net effect over time. And in this case, it's kind of this small eroding around everything. Yes, you see the big iceberg calving event, but I think more interesting is the unnoticed changes that are happening everywhere else. And you actually see this in Greenland as well, where you get this kind of continual eroding around the edges of the ice shelves. And I think that really points to ice shelves that are out of balance with the mean climatology. And so, yes, you have these big rifting events, but there's also something else going on. And Chad covers that in detail in his paper. And then you have, the It's Life product. So this is the project that I'm leading. And on the right, I'm just showing an online widget that you can go and play around with. Go to the It's Life website and you'll find information about it there. And what I wanted to show with this animated GIF on the right there is just simply how data access has changed. And so, this online tool is operating in real time, and you can get these velocities for tens of thousands of points, if not hundreds of thousands of points, within seconds just by clicking points on a map. And if you think back to 2011, that was when we had our first complete mapping of Antarctic velocity. So in 10 short years, we've gone from a single really revolutionary mapping of just what is the flow of the ice sheet. And now we're moving to, kind of an everywhere mapping, a detailed history of ice flow. And this is really going to help, hopefully, accelerate our understanding of the processes. And so this It's Life project, there's currently 12.5 million image pairs in the archive that you can just access through the click of a button. And it represents terabytes of data. And each day there's 9,000 new image pairs to derive velocity from. And so this record is only going to grow, and our understanding of the changes is only going to grow. And here's an example of a different way of looking at that data. So you can actually take that data and, it can be noisy in places. There's just limits to how well the sensors operate in all these different regions. But when you build up tens of thousands of points for each place on over a glacier, you can really start to beat down the noise and look for all of the subtle signals. And so what's plotted here, this is actually a map that Chad Green put together. What's plotted here is actually the seasonal amplitude and phase. So we've subtracted the mean flow, and we're just looking at the seasonal velocity and its phase. So its timing within the year. And you can imagine that this is essentially what you're looking at is the seasonal waves propagating up and down the glaciers. And this will, once we have time to think hard about how to extract meaning from this, it's going to tell us a lot about basal sliding laws and how those are being modified with changes in meltwater input. And, the observations are driving improvements. I don't think maybe fast enough. I think the data for the first time in, the history of glaciology, the observations are outpacing the rate at which we can derive the science. And so we're becoming awash in data, and now we need to think of new and clever and creative ways to derive better understanding from that. But I just wanted to highlight a couple studies. And, again, this isn't exhaustive. There's lots of other people who have done amazing work, but there's just a couple things I wanted to point out here. One is kind of a seminal piece of work by Brent Menchu, who looked at tidal variability and ice flow for the Rutherford ice stream. And, because he had such a dense record, was able to really understand the mechanics of what was going on there. And all of its interesting behavior with the tidal velocity waves propagating upstream of the grounding line. And then Ian Jochen published a really great paper where he used the longer record of ice flow and then ran a forward model using different flow relations, and was able to make an argument that, really a regularized Coulomb friction law is the most appropriate for modeling ice sheet sliding of the Pine Island Glacier. And that's incredibly important because which law you choose to parameterize your friction at the base of your model has a large influence on how the model will evolve in the future. And then there's a study that's gone a little unnoticed, I think, and this is by Victor Tsai at Brown University. And I really think he's nailed it. He's published this incredible study where, with an incredible data set, where Lawrence Smith had some GPS records and a lot of input, a lot of data on moulin input, so the amount of water flowing into the moulins. And Victor was able to create a very convincing model that really combines already known principles, but combines it in a way where it matches intuition, and it also matches the observations incredibly well. And so I'd encourage you to go read that if you're interested. And so what I'm trying to highlight here is it's really the data. The data is allowing people to answer those challenging questions and to be able to validate them against the observations and make progress in the field. So now I'll talk about upcoming missions for NASA. Okay, so one of the missions I'm most excited about that's probably the closest to launch in terms of relevance to ice sheets is the NISAR mission. The NISAR mission is a collaboration between the Indian Space Agency, ISRO, and NASA, and it is a combined L and S band synthetic aperture radar. It has a very high resolution and large swath, and this is only achievable because of this sweep SAR mode. And that sweep SAR mode is actually shown on the right. And it's a beautiful and complicated diagram, but it shows how you can resolve in the across track direction using this sweep SAR technique and this massive antenna. I think it's a 12-meter antenna that will deploy from the spacecraft. So it's a marvel of engineering, and it will be a really revolutionary data set. This will not just be another SAR, this will be the first SAR that we have seen like this. And L-band in particular promises much higher temporal correlation, and so we should be able to get much better velocity fields. The other big benefit is that the decision has been made to make NISAR a left-looking SAR instrument. And so this means that it is going to have much more South Pole coverage than North Pole coverage. And so it is going to reach routinely, so that's every orbit, it will be collecting data all the way up to 87.5 degrees south, which is all of the grounding lines. And that will be repeating every 12 days. But of course, as you get to the poles, you'll have much, much more dense coverage than that. And this will provide a step improvement in the accuracy of ice flow and provide a lot more detail in subtle changes in the ice sheet. Another mission that's coming up, this has just gone, I think there was just a selection made. I'm not quite sure, but I believe it's going to actually be a constellation of satellites as opposed to one monolithic satellite like all of the other Landsats have been. This will actually be a constellation. And it's going to be a radical change from what's been done in the past. And so instead of the 11 bands that were on Landsat 8 and 9, Landsat Next will have 25 bands. And so there'll be a lot more spectral information in the data that we'll be able to derive meaning from. And, things like snow melt and ice melt will be there, and also feature tracking to derive velocity. And then looking further out, there's a few missions that are in the works. One is mass change. I don't actually know the launch date for mass change, but this will be a continuation of Grace Follow On, and this will be the next version of that. And from what I know, it will look very much like Grace and Grace FO. There's also a surface deformation and change. The concept study is underway for that. And that will be the follow-on mission to NISAR. So that'll be an INSAR mission. And then there's also another mission called Surface Biology and Geology that will be relevant to cryosphere, and that will be a hyperspectral mission. And so that'll be, help us with better understanding the snow physics and melt characteristics and those types of things. So those are designated observables. Those are slated to go through sometime in the next decade. And then there's also Earth Explorer missions. These are smaller missions, and they're competed. And so there's 7 Earth Explorer missions that have been identified, categories that they want to see competed missions for. And one of those that is relevant to ice sheets is an ice elevation. So there is no laser altimeter mission like ISAT-2 that is lined up to launch. But this Earth Explorer, if it's able to compete, there's only one selected in the first round. So it's going to be one of 7 that will be competed. So fingers crossed. And then the next thing I wanted to talk to you about was an ice sounding mission concept. There was an ice sounding mission concept that was submitted through NASA called through their Earth Venture program, EVM, Earth Venture mission, and it was called Deep Ice, and it was a single VHF sounding spacecraft. And unfortunately, that mission wasn't selected. But there is another concept that's being developed right now at JPL on behalf of NASA. And this is actually an externally sponsored mission. And so the Qatar Foundation and Qatar itself have made a commitment to contribute towards the better understanding of climate change. And when they hosted the COP a few years ago, they committed a large amount of money to contribute to understanding climate change. And one of the things they're thinking about doing is possibly launching a mission in collaboration with NASA, where they would provide the funding and NASA would help develop the engineering and oversee the mission. And Qatar has agreed that if this mission was to go forward, all of the data would be publicly available, like any other NASA mission. And so it's really exciting. I mean, there's the potential here that we might actually get a nice sounding mission. Okay, so a lot of people they have this preconceived idea that Qatar, it's a desert nation. It is so far away from the ice sheets. Why would it care about sea level rise and changes in the desert? Because this mission can also be used to look for deep aquifers. So, deep aquifers in North Africa and the Arabian Peninsula, that intuitively makes a lot of sense. But what a lot of people don't realize is that Qatar is an incredibly low-lying nation. The median elevation of Qatar is 25 meters, with about 80% of its population living within 10 meters of sea level rise, within 10 meters of present-day sea level. And so it's a nation that's highly vulnerable to changes in sea level. It's this small sand spit that is vulnerable to sea level. And they're also interested in exploring North Africa and the Arabian Peninsula water resources. And I'll talk a little bit about that, but not much. Qatar also wants to contribute to science impacting global humanitarian causes. and comprehensive airborne missions. They're really not practical over the deserts or over the ice sheets. So here's a look at what the proposed concept is. It's actually a constellation of satellites. So you have one satellite in the middle. It's called the mothership. It has the transmitter, and it also receives, and it has a 11 or 12 meter Yagi antenna that's pointed to the ground. And then it has 4 daughter sats that are continually orbiting in a circle around the mothership. And what this allows is that when the daughter spacecraft align in the across-track direction, it allows you improved focusing in the across-track direction. And so improved clutter rejection over the ice sheets and over the deserts, which is really important. And then also it allows you a smaller footprint because you get some cross-track focusing. And so I'm just going to run this animation here. It's really insightful because it's hard to envision how the satellites orbit around each other. So the view from above is that circular orbit for those different spacecraft. And then when you look at the view from behind, so that's the bottom right, you can see the way that this is done is by slightly varying the altitude of the spacecraft, of the daughter sats, so that they get this slightly elliptical orbit around the mother sat. And these would be spaced out on the order of 200 meters, I believe, on either side. So OASIS is going to accomplish science over the ice sheets, and that the science is really focused on ice sheet sounding. So just trying to measure the thickness of the ice sheet. That's kind of its sole purpose there. It will do this over both Greenland and the Antarctic. And it's also going to look for the presence of shallow water aquifers in the Arabian Peninsula and North Africa. And what people often don't know is that North Africa and the Arabian Peninsula are actually underlain by huge aquifers that formed, tens to hundreds of thousands of years ago when the climate was different. And so they're all underlain by aquifers. And some of that water reaches the surface through artesian flow, so the water's under pressure and it finds its way to the surface. And that's why you can find an oasis in the middle of a desert. It's because the water's actually flowing up through those aquifers. And those will be found in lower depressions or basins that are underneath the desert, right? The desert isn't, hundreds of meters of sand in most places. It's usually, few tens of meters of sand that overlie bedrock. And so there's chances for aquifers under there. And there's signs of evaporites and visibility of oasis, water at the surface that give indications that there is some water there. But that is going to be done mostly experimental. And so what's being proposed right now is this concept where you have a mother sat and you have these 4 daughter sats. And the daughter sats are being considered as a technology demonstration. This is something that NASA hasn't done with an active sensor yet. And so this would be really novel to be able to fly a constellation of radars, especially at this low frequency. The requirements over the Antarctic, those are science requirements. And so, we're very confident at what we would be able to retrieve in terms of ice thickness for the Antarctic ice sheet. Over the deserts, there's a lot of challenges. It primarily has to do with a lot of surface clutter, and we're looking at the surface in terms of changes in the amplitude of the first return. And so we're doing reflectometry. We're not actually doing sounding over the deserts. And that's because there's higher attenuation losses in the deserts than there are over the ice sheets. And so sounding gets much more difficult. Of course, you're operating the instrument in the same way. And if there is any ability to do sounding over the deserts, we'd be able to do it. But that's not something that we're promising. And then over Greenland, it will be a science goal. And that's simply because, there's more meltwater. We expect higher attenuation over Greenland, higher surface roughness, and so there's more challenges there, but we will operate the instrument if the mission was to go forward over Greenland and collect observations. Okay, so for the ice science investigation, I've already mentioned this to you, that the Antarctic ice sheet accounts for a huge amount of the uncertainty in sea level rise. That's so if you want to try and improve estimates of sea level rise, you should really focus on the Antarctic ice sheet. And probably the most significant contribution we can make in terms of observations is just improving the bedrock. It's a one-time observation that provides a boundary, a critical boundary condition for ice sheet models, to the point where ice sheet models are not going to be doing a good job without a good boundary condition of basal topography. And so we're really curious in how the ice sheet is going to change as the ocean warms. And I think most interesting to this group is, here's current coverage on the left. I think it's about 23% of the ice sheet when gridded at 2 kilometers has some sort of observation of ice thickness. And the OASIS coverage that we would get after 18 months in orbit, it would be a drifting orbit. The coverage looks like you see in that middle figure, so we get incredible coverage. And lastly, on the right-hand side, you see the uncertainty, which just comes as a function of distance from observation. And so there's still huge uncertainties that remain in the ice sheet. Now, full disclosure, that figure in the middle of the orbital coverage is certainly not what we expect to get. I think the expectation is that about 25% of the ice sheet is what we can retrieve. 25% of the observed area is what we'll be able to retrieve from space. So we would be doubling our knowledge in ice thickness. And then there's also limitations about where these observations can be made. And this part is really important, is that I really don't think this mission conflicts at all with Ring's efforts or a desire for improved bed topography, because essentially where you are unable to measure from space because you're going to be blinded by the clutter is in areas of steeper topography or high crevassing. And so that's all around the coast. A satellite mission isn't going to be able to observe. But as soon as you get it kind of into the smoother interiors, which are very difficult to access with an aircraft, then you'll be able to use a satellite. And so I think the solution to mapping the bedrock in the Antarctic is really a combination of airborne and satellites in order to be able to make these measurements and complete the maps that are so desperately needed. And this is a really compelling figure that was really the brainchild of Blake Castleman and Nicole Schlegel, Eric Leroy, and Mathieu Morlahan. And what they did here is they took bed machine and they took the errors from bed machine and took the 3 sigma errors and put those in to an ice sheet projection, so into ISSM, and they ran the model forward with those elevations added and subtracted, so the error bounds. And then, working with the radar team, we simulated what the expected error from bed machine will be after OASIS is to fly. And so once you add all those additional observations, and now you have a reduced uncertainty, and you put those into ISSM and see what the spread is in projected sea level. And so this is purely looking at the intrinsic uncertainty due to the bedrock. And so we're not looking at all of the other extrinsic sources of uncertainty. So there are certainly more sources of uncertainty. But what this shows is that an 18-month mission could greatly improve our understanding or ability to project sea level into the future. And this would be even more critical if we had observations right around the coast from a series of airborne campaigns. And so it just shows, it's a great example of how valuable bed topography is for improving projections of sea level change. And I encourage anyone who hasn't to go read Blake's paper. It's in the cryosphere. It's focusing mostly on the Thwaites Basin, but it really shows a good logical, quantitative study of how improving bedrock can improve projections of sea level change. Okay, so now to wrap it up, ice sheets are very predictable. If there's anything in the Earth system that we should be able to predict, it should be the ice sheets. These are systems with huge amounts of momentum. It doesn't have any turbulent flow. If we have a hope of predicting anything or projecting anything, it really should be the ice sheets. But we need to make progress at a rate faster than the ice sheets are evolving themselves. And one very humbling study, was done all the way back in 1978 and published in Nature, saying that that if CO2 concentrations are to double, that it is highly likely that the West Antarctic ice sheet could collapse. And I think we are at the same place in our knowledge. So all the way back in 1978, they were fairly close to the understanding that we have now. And sure, ours is more sophisticated, more complex, but I'm not sure if we can say a lot more than we could back in 1978. And so I think, we still have a ways to go to overcome those last hurdles that have been so challenging to overcome. And this slide I'm going to skip because we don't have time. And lastly, I'm just going to give my opinion on what I think needs to be done to accelerate our understanding of sea level change, or the predictability of ice sheet change that is really governing sea level change. And this is my own view. 10 years post PhD of kind of what I've settled on is what really needs to happen to accelerate our understanding of these processes. So. I think that we really need to continue the synthesis of these key data sets to generate higher level analysis ready data sets. I think too much of our time of our PhDs is being wasted on playing with the data as opposed to trying to generate science from the data. And I know sometimes they go hand in hand, but I think there's a lot of science that can be done without needing to spend so much brain power in understanding the observations. And so I think that we really need no barrier access, cloud-hosted data sets. This is all just an engineering problem. I don't think that every researcher should be writing a script to bring in all of the data, align it geographically, and then co-align it in time, and be having to do all of that before they can get their work done. They should be able to just click on a point on a map, get their data, and start answering their science question. I think we can really make the scientific community more efficient if we do things like that. I think that the glaciology community really needs to embrace more advanced data science techniques. The commercial sector is now moving to Earth observations, and they are unleashing some of the talents that they have learned over the years for applying AI and ML techniques to other more profitable problems, and now applying it to Earth observing data sets. And what they are showing is incredibly promising. And yes, it can't answer all of our questions, but I think as a community, we should really embrace it and try and learn more to see where it can help us out to accelerate models, to invert for unknown parameters in physics, and to generate these kind of continuous records that we can use to force our models and make sure that we have the right physics in the models. I think we need improved knowledge of shelf ocean properties. So that would come through ships and gliders. We still have really poor understanding of the shelf water properties around the Antarctic. We need much better bedrock topography under the ice sheet and under the ice shelves. Without the bedrock topography, we don't have a hope of generating reliable projections. And then we also need improved bathymetry mapping around the continent. We need to know where the warm water is able to access the ice shelf, and also to be able to forward model what we anticipate to happen in the oceans. We need further advancement in ice sheet modeling and data assimilation. There's a lot of work going on this, and I know Mathieu has been at the forefront, and I'm sure he could use as much help as he can get. And then we need processes that are keenly focused on advancing the understanding of those critical processes to improving sea level change. And so, that list I had before, I think we really need to try and put more focus on those specific topics because our advancement will be limited until we overcome those. Anyway, that's everything. I hope you enjoyed it or at least got something out of it. I'm sure you've heard a lot of this before. I thank you very much for giving me the opportunity to speak. And again, I really wish I could be there to share a beer, but have a beer in my honor. Thank you very much.